Welcome to the sixth session on moment distribution method and myself Vahini M. In this session we are going to analyze non-sway frames. So let us take up a non-sway frame as shown in the figure ABCD. Okay, so ABCD is a non-sway frame. Why it is a non-sway means we have a support at the beam level, therefore the frame will be a non-sway frame. Okay, so as usual the first step is to find the distribution factors, to find the fixed moments. So MFAB, it is subjected to UDL throughout, therefore it is calculated by minus WL square by 12. Substitute the value of W as 20, intensity of UDL, L is the span, so if you substitute it, it will be 20 into 4 square by 12. So that will be equal to minus 26.67 kilonewton meter. Next, MFBA is calculated by plus WL square by 12, and that will be equal to 20 into 4 square by 12, which is equal to plus 26.67 kilonewton meter. Next, MFBC. BC is subjected to an eccentric point load. The point load is at a distance of 2 meter from end V and 3 meter from end C. MFBC is calculated by the equation minus WAB square by L square, where W is the magnitude of the point load 40, A is distance of the point load from the left end, that is 2 meter, and B is distance of the point load from the right end, that is 3 meter, and L is span of the member. So if you substitute it, it will be 40 into 2 into 3 square by 5 square, WAB square by L square. So that will be equal to minus 28.8 kilonewton meter. Next, MFCB is calculated by WBA square by L square. W, again the magnitude of the point load, B is distance of the point load from the right end, that is 3 meter, and A is distance of the point load from the left end, that is 2 meter. So if you substitute it, it will be 40 into 3 into 2 square by 5 square, that will be equal to plus 19.2 kilonewton meter. Next, MFDB. So that will be, BD or DB member is subjected to a central point load, therefore it is calculated by using the relation WL by 8. So you can ask, why DB is taken as negative, why not BD? Because if you rotate the vertical member BD or DB in such a way that this load will be acting in the downward direction. You just rotate the BD vertical member in such a way that it will be acting in the downward direction. The load will be acting in the downward direction. So to make this load act in the downward direction, we have to rotate this BD member in the clockwise direction. Then D will be the left end. D becomes the left end and B becomes the right end. Therefore, it is taken as minus WL by 8. So same thing, W stands for the magnitude of the point load 20, L is span of the member BD. So if you substitute it, minus 20 into 4 divided by 8. So that will be equal to minus 10 kilonewton meter. Similarly, MFBD is calculated by plus WL by 8, and that will be equal to plus 10 kilonewton meter. So that is about the fixed end moments. So next step is to calculate the distribution factors. So we know that distribution factors are calculated for the intermediate joints. So in this frame, joint B is the only intermediate joint we have, and the members meeting at B are BA, BC and BD. So there are 3 members meeting at joint B. So A and D, the far ends A and D are fixed, therefore the relative stiffness will be I by L, whereas C is a roller, therefore the relative stiffness will be 3/4 of I by L. So next, the distribution factors are calculated in the form of a table. So first column is joint, second column is member, third column is relative stiffness, fourth column is total stiffness, and the fifth column is distribution factor, which is the ratio of relative stiffness of a member to the total stiffness of the joint, that is K divided by sigma K. So the joint, we have the intermediate joint as the only joint B. So the member meeting at joint B, let us take it as BA. So the first, let us consider the member BA. So as I have already explained, the far end A is fixed. Therefore relative stiffness is calculated by I by L. So I is 1I and length of the member BA is 4 meter. Therefore I by 4, that will be equal to 0.25 I. Okay. Next, for BC member, next member is BC. So BC member, the far end C is a hinge, a roller. Therefore the relative stiffness is calculated by 3/4 of I by L. So it will be equal to 3/4 of I divided by the length of the member BC is 5 meter. So that will be equal to 0.15 I. Next, for member BD, again D is the far end, which is a fixed end. Therefore I by L is the relative stiffness, which will be equal to I by 4, and it will be again equal to 0.25 I. So next column is the calculation of total stiffness, which is the summation of relative stiffnesses of all the members meeting at joint B. So that is 0.25 I plus 0.15 I plus 0.25 I. That will be equal to 0.65 I. That is the total stiffness. Next, distribution factor for member BA. It is calculated by relative stiffness for member BA to the ratio of total stiffness at joint B. Okay, so that is 0.25 I divided by 0.65 I. So that will be equal to 0.385. That is the distribution factor for member BA. Next, distribution factor for member BC is calculated by relative stiffness for member BC to total stiffness of the joint B. So that is 0.15 I to 0.65 I. That will be equal to 0.23. So distribution factor for member BC is 0.23. Next, distribution factor for member BD is calculated by the ratio of relative stiffness for member BD to total stiffness of joint B. So that is 0.25 I divided by 0.65 I. That will be equal to again 0.385. So these are the distribution factors for BA, BC and BD. So if you add all these three, 0.385 plus 0.23 plus 0.385, it will be equal to 1. So the next step is to distribute the moments. So the distribution is carried out in the form of a table. So the first row is the joint. So that is the joints coming under the different joints of the frame are listed in the first row. That is joint A, B, C and D. So the second row is the members coming or meeting at different joints are listed in second row. Under A we have got member AB. Under joint B we have got 3 members meeting at joint B, that is BA, BC and BD. Under C we have member CB, and then under D we have member DB. So next we have to write the distribution factors. So distribution factors for the intermediate joints are, for BA it is 0.385, for BC 0.23 and then for BD it is 0.385. Next row is the fixed end moments. Okay, so the fixed end moment for AB, MFAB is minus 26.67, MFBA is plus 26.67, MFBC minus 28.8, MFBD plus 10, MFCB plus 19.2 and MFDB we have minus 10. Okay, so if you look into the frame, C is the roller. Okay, so first we will balance the roller support, that is joint C. So next step is to balance the roller support. So we know that the final moment at joint C will be 0. Therefore, to make it as 0, we will apply a moment of minus 19.2. Okay. So as soon as we apply a moment of minus 19.2, half of the moment will be carried from CB to BC. It will be carried from CB to BC. How much? Half of this 19.2. So that is minus 9.6. So at this level we will make a total, so that we will make joint C as 0. Okay. So MAB minus 26.67, MBA plus 26.67, MBC minus 38.4, MBD plus 10, MCB it is 0 and MDB it is minus 10. So next we have to balance the intermediate joints. So next step is to balance the intermediate joints. So the intermediate joint is joint B. So what is the imbalancing moment at joint B is 26.67 minus 38.4 and then plus 10. So the imbalancing moment at joint B is minus 1.73. So the balancing moment will be plus 1.73. So that plus 1.73 will be distributed among the members meeting at joint B, that is BA, BC and BD, according to their distribution factors. Yes. So 1.73 into 0.385 will be 0.666, which is the moment carried by member BA. Next 1.73 into 0.23, that will be equal to 0.398. That is the moment which is carried by member BC. And 1.73 into 0.385, again it is 0.666. This moment which is carried by member BD. So that is balancing of joint B. So as soon as we apply a moment of 1.73 at joint B, so some portion of the moments will be distributed or carried by the far ends from BA to AB. So the next step is carry over from BA to AB. Half of this 0.666 will be carried from BA to AB. That is half of 0.666 will be equal to 0.333. Similarly, from BD to DB, it will be carried from BD to DB. Why? Both A and D, they are fixed. Therefore, they will take the carry over moment. Whereas C, it's a roller, therefore it cannot take the carry over moment because the final moment itself is 0. Okay. So therefore, the half of 0.666 will be again equal to 0.333. This is the moment carried to member DB. So next, what is the next? Next cycle, balancing and carryover. So here there is no balancing because we have only one member, one intermediate joint. So that joint is balanced now and the moments are carried to the far ends, and far ends are fixed. So there is no further step to carry. Therefore, we can finalize at this stage and go for calculation of the final moments. So the final moments are calculated as the summation from the total row. Okay, we have to add all the values in each column from the total row. For AB, minus 26.67 point plus 0.333, that will be equal to minus 26.337. Next, for BA, 26.67 plus 0.666, that will be equal to 27.336. Next, minus 38.4 plus 0.398, that will be equal to minus 38.002, and 10 plus 0.666 will be equal to 10.666, and for CB it is 0, and then for DB minus 10 plus 0.333, that will be equal to minus 9.667. So you can check whether the joint B is balanced or not. You can add all the values, final moments at joint B, that is 27.336 minus 38.002 plus 10.666. That will be exactly equal to 0. So that means sigma MB, if you apply sigma MB at joint B, that is 0. Okay, so now we have balanced joint B. Okay, so these are the final moments at joint A, B and C and D. MAB minus 26.33, BA 27.336, BC minus 38, BD 10.67, CB 0 and for DB it is minus 9.67. So these are the final moments using which we will find the support moments. So the next step is to calculate the support reactions. Sorry, we have to calculate the support reactions. So reactions are calculated by considering each span separately. So first let us consider AB member. So with the end moments, since end A is a fixed end, let us consider HA and VA as the reactions, and at B we have member VB1. So MAB is minus 26.337, therefore it is shown in anti-clockwise direction, and MBA is plus 27.336, therefore it is shown in the clockwise direction. So now let us apply the conditions of equilibrium, that is sigma Fy is equal to 0. That is algebraic summation of forces in y direction are taken as 0, which implies VA plus VB1 is equal to 20 into 4, that is equal to 80 kilonewton. Next, we will take moment of all the forces about A and equate it to 0. So the sign convention is clockwise moments are taken as positive. Therefore, minus VB1 into 4. Why minus? Because it is inducing anti-clockwise moment about A. So minus VB1 into 4 plus 20 into 4 into 2. So this UDL, if you convert it into a point load, that will be acting at the center of the span. So 20 into 4 is the magnitude of the point load into the half of the member length, that is 2 meter. 20 into 4 into 2 plus 27.336 minus 26.337. So if you calculate it, you are going to get the value of VB1 as 40.25 kilonewton. Then substitute back into this equation so that we can get the value of VA as 39.75 kilonewton. So that is the reactions for AB member. Next we will move to member BC. So member BC, so C is a hinge, therefore there is no support moment. We have got reaction at C as RC and a reaction at B as VB2. Okay. So let us apply sigma Fy is equal to 0, which implies VB2 plus RC is equal to 40 kilonewton. Next, take moments of all the forces about B and equate it to 0, which implies minus RC into 5 plus 40 into 2 minus 38.002. That will be equal to 0. Hence, RC is equal to 8.4 kilonewton. And the value of VB2 will be 31.6 kilonewton. So reaction at B is calculated as the summation of VB1 and VB2. So if you substitute the values of VB1 and VB2 as 40.25 plus 31.6, so the total reaction at B is 71.65 kilonewton. Let us consider the vertical member BD. So BD along with the loading and the reactions are shown in the figure. End moments along with the end moments. So let us apply sigma Fy is equal to 0, which implies VD minus RB equals 0. Therefore VD will be equal to RB, that will be equal to 71.65 kilonewton. Next, let us take moment of all the forces about B and equate it to 0. So which implies HD. So this HD is inducing clockwise moment about B, so HD into 4, and 20 kilonewton is inducing anti-clockwise moment about B, therefore minus 20 into 2 plus 10.666 minus 9.667. So that will be equal to HD is equal to 9.75 kilonewton. 9.75 kilonewton. Okay. So next, let us consider the entire frame along with the horizontal reactions HA and HD. So apply sigma Fy for the entire frame. Fx is equal to 0 for the entire frame. So which implies HA minus HD plus 20 is equal to 0. So that will be equal to HA minus 9.75 plus 20 is equal to 0. So that will be equal to HA is equal to minus 10.25. So minus means whatever the direction we have assumed, it is wrong. So the actual direction is opposite to what we have assumed. So that we will correct in the next slide. The direction will be shown correctly in the next slide. Okay. So these are the reactions using which we will plot the shear force diagram. So in the next slide, we will take up how to draw the shear force diagram for the given frame. So now, so you can look here. So the direction of HA is changed. Okay, so the frame along with the reactive components are considered here. So HA 10.25, VA 39.75, RB 71.65, RC 8.4, and HD 9.75, and VD 71.65. Okay, using these applied forces and reactions, we will plot the shear force diagram. So to draw the shear force diagram, consider the base structure without the supports as well as the applied loading. So similar to the beam. Okay, we will draw the shear force diagram for the beam member. Okay, so shear force to the left of A 0, shear force to the right of A, and we have an upward force of 39.75, therefore draw it in the upward direction for 39.75. Next, shear force to the left of B, we have a UDL in between A and B, therefore you have to deduct that one, so whose magnitude is 20 into 4. So plus 39.75 minus 20 into 4, that will be equal to minus 40.25. That is the shear force to the left of B. Okay. So next, shear force to the right of B, we have the reaction of upward reaction of 71.65. Therefore minus 40.25 plus 71.65, that will be equal to plus 31.4. Plus 31.4. Okay. So then shear force to the left of E, let us consider this as point E. So shear force to the left of E, we don't have any forces in between right of B to left of E, therefore shear force will be constant till that point. And then shear force to the right of E, we have a downward force of 40 kilonewton. So plus 31.4 minus 40, that will be equal to minus 8.4. So in between right of E to left of C, we don't have any forces, so therefore shear force will be constant up to that level. And then shear force to the right of C, we have an upward force of 8.4 kilonewton. So therefore minus 8.4 plus 8.4, that will be equal to 0. Okay, so this is the shear force for the beam member. So now comes the question of how to draw the shear force diagram for the vertical member. Okay, so the positive shear forces are drawn to the right side of the vertical member, and negative shear forces are drawn to the left side of the vertical member. Okay, so how to consider the given forces are positive or negative. Okay, whereas in the horizontal member we have a sign convention of upward forces as positive and downward forces as negative, whereas for vertical member we have another sign convention, that is the forces are inducing clockwise couple, then it is a positive shear force. Okay, and if the forces are inducing anti-clockwise couple, then it is a negative shear force. That is the sign convention for vertical member. Okay, so let us draw the shear force diagram for the vertical member BD. Okay, so to draw the shear force diagram for vertical member, let us first divide this 20 kilonewton into two forces of 9.75 and 10.25. So if you add these two, it will be equal to 20 only. Okay, so we have divided the given force of 20 kilonewton into 9.75 and 10.25. So let us neglect this 10.25 for a while. Okay, and now if you consider this HD of 9.75 and this 9.75 kilonewton, these two forces are equal, opposite and parallel forces. Okay, so these two will induce what type of couple? They are inducing clockwise couple. Therefore we have a positive shear force. Therefore it has to be drawn to the right side of the vertical member for 9.75. Okay, and then so till this level we don't have any forces, it will be constant till that level. Okay, next let us consider this 10.25, and so by the application of principle of superposition or transmissibility, we can take it as transmissibility. So this point of application of HA, we can transfer this along this line of action to joint B. Okay, from A to B. Okay, so that is what this B here. Okay, so I have transferred from A to B the reaction HA. So HA is in this direction of 10.25 and we have this assumed force of 10.25. Okay, so these two forces again equal, opposite and parallel forces. Okay, so these two are inducing what type of couple? They are inducing anti-clockwise couple. Okay, so therefore we have a negative shear force of 10.25 kilonewton. So this ordinate should be 10.25. Okay, negative shear force of 10.25, and then we don't have any forces in between B to F. We can take it as F. So in between B and F, therefore it will be constant till B. Okay, so this is the shear force diagram for the vertical member. Okay, and these are the positive shear forces. So upward forces are positive for beam member and the forces towards the right side of the vertical member are positive. Okay, and these are the negative shear forces. Downward forces for the beam member are negative and the shear forces to the left side of the vertical member are negative. Okay, so vertical member shear force is drawn in red color so that we can differentiate it easily, and for the horizontal member it is drawn in black color. Okay, so this minus in black is for the beam member and this red minus is for this vertical member. Okay, this is the shear force diagram. Next we will draw the BMD and elastic curve. To draw the bending moment diagram and elastic curve, consider the base frame along with the end moments. Okay, so BA, BC and BD. Draw the base structure similar to that of the given frame. Okay, so this use the thumb rules as similar to the previous problems. For the left end, left thumb, and right end, right thumb. So at left end we have a anti-clockwise moment which indicates the thumb movement in the upward direction, so mark it above the baseline for 26.34, and at right end we have clockwise moment, so use the right thumb, again it is moving in the upward direction, so mark it for 27.34. next for BC, join these 2 points. Okay, next for BC it is anti-clockwise, left thumb, again it is moving in the upward direction, so at the same point mark it for 38. It was 27.34 earlier for BA and now for BC it is 38. Okay, so the line extends till 38. Okay, and at C it is 0, so therefore join from 38 to 0. This is the support moment diagram for horizontal member. Next for vertical member, so use the thumb rules. The thumb is moving towards left side of the vertical member, so mark it towards the left side of the vertical member for 10.66. Okay, so I have marked it in the red color so that you can differentiate it. Okay, and then again the moment at D, again it is moving in the left direction, so you have to mark it in the left direction for 9.667. Okay, so join these 2 points. Okay, so this is the support moment diagram for this vertical member. Okay, so over which we will superimpose with the free bending moment diagram. AB is subjected to UDL throughout, therefore it is subjected to a parabola with highest ordinate as WL square by 8, which will be equal to 40 kilonewton meter. W is 20, L is 4 square divided by 8, that will be equal to 40 kilonewton meter. Next, BC is subjected to eccentric point load, therefore the shape of free bending moment diagram is a triangle with highest ordinate under the point load as WAB by L, which will be equal to 48 kilonewton meter. So W is 40, A is 2 and B is 3 divided by 5. 40 into 2 into 3 divided by 5, that will be equal to 48 kilonewton meter. Next, for member BD we have a central point load, therefore the variation of bending moment diagram will be a triangle with highest ordinate at the center as WL by 4, which will be equal to 20 into 4 by 4, again it will be equal to 20 kilonewton meter. So this is the bending moment diagram, and the points where free bending moment diagram crosses the support moment diagram, they are called as points of contraflexure, where the bending moment value will be 0. Okay, so these are the sagging moments, positive moments, and other ones are negative moments. They are support moment diagrams. Support moments, they are always negative. Okay, so this is the bending moment diagram for the given frame. Next, to plot the elastic curve, consider the base frame without loading and with the supports. Okay, so the variation of elastic curve will be similar to as that of the bending moment diagram. So at supports the moment will be hogging, and at the mid spans the deflection will be sagging. Okay, so for AB member at the mid span the positive moment dominates, therefore the beam sags in the downward direction, and at support B the negative moment dominates, therefore this hogging moment dominates. So at C it is 0, therefore deflection will be 0 at the joint C, and so at the mid span of the vertical member sagging moment dominates. So this is the variation of elastic curve. This is how you have to draw the elastic curve for the given problem. So this is about the analysis of non-sway frames. Okay, so in this session we have studied how to analyze a non-sway frame, especially orthogonal frames. Okay, so these are orthogonal, means the frame members are at 90 degrees to each other. They are not there are no inclined members. Okay, so you have to judge on your own whether the given frame is a sway frame or non-sway frame. Just look into the given frame. If you have any supports at the beam level, then that type of frames are treated as non-sway frames. If there are no supports, maybe fixed or a hinge, okay, only if it is a fixed or a hinge, then only you can take those frames as non-sway. Why? Because if you have a fixed or a hinge, there will be a reaction, horizontal reaction, which will avoid the sway of the frame. Okay, so that is lateral displacement of the frame, that will be avoided by this horizontal reaction. Okay, if a fixed end or a hinged support is provided at the beam level, then you can take those frames as non-sway frames, and you cannot take a frame with the roller end at the beam level as a non-sway frame. Okay, so because we don't have any horizontal reaction for a roller, provided if the roller is supported in the vertical direction. So here the reaction is in the vertical direction. If the roller is rotated in 90 degrees, then the reaction will be in the horizontal direction. In that cases, you can take that frame as non-sway frame. Okay, so judge the given frame. If it has any reactive component in the horizontal direction, you can take that frame as non-sway frame. Okay, so that is for today's session. So in the next class we will take up one more problem on non-sway frame. Thank you.